The last part of this first module is the evaluation of the properties of manufactured products. That is the one component I will try to cover in this part, and second one is the statistical and data driven modeling approach normally we follow if we collect some data. So, these two part we will try to cover. First look into that properties evaluation. So, we have some already discussed about the different properties normally we will consider to test the quality or performance of a manufactured product, but how we can conduct these experiments just to get some overall view on that. So, properties evaluation in the sense that basically characteristics of the sample by different experimental techniques, and then how we can do that, we can do either to evaluate the physical properties, for example density, melting point, optical properties, thermal expansion of the thermal properties of the specific heat, coefficients of the heat transfer, thermal expansion, conductivity, electrical conductivity, magnetic properties. These all are the physical properties. There is a standard methodology, and that following the standard methodology test methods we can evaluate all these properties, but this properties is more important before doing the before applying the applying or before applying any manufacturing processes. But once we apply some manufacturing processes to modify to get certain product, and after that then we can evaluate the other properties. For example, in most of the cases we test the microstructural characterization, and then for microstructural characterization normally we follow the using the optical microscope or maybe high resolution microscope, scanning electron microscopy, or in some cases some properties we can evaluate simply using the principle of the X-ray diffraction technique. So, these are the other techniques we normally evaluate the properties in a manufactured component, or of course now out of these properties one by one we will try to discuss this thing. First we look into the mechanical properties. This is the most commonly used mechanical performance of a manufactured component. To evaluate that we do the mechanical testing, and then mechanical properties can be evaluated in the either in the static properties. We can evaluate the static properties. For example, if we apply the uniaxial tensile testing facility, and there we use some standard size of the specimen, and then once the standard size of the specimen according to the different standardization techniques, and of course the size effect we normally produce uniaxial tensile testing, we can represent the load versus deflection data when we conduct the uniaxial tensile testing of a sample, but the size effect can be eliminated by using that load divided by the cross sectional area of the sample, and of course the deflection, what is the deflection or deformation happens that with respect to the original length. If we make the relative measure of these things in that way, then we can eliminate the size effect, and then that normally represented in terms of the stress strain curve. So, that means stress is defined simply the load divided by the original cross sectional area, and strain which is defined by change in the length, say L1 minus L0 with respect to original length. So, that stress and strain we can represent, and of course that is size effect can be eliminated, and that is compared as compared to the load versus deflection curve in uniaxial tensile testing. So, what information we can get from the stress strain diagram or mechanical testing of a sample. So, the characteristic information from the stress strain diagram we can evaluate the proportional limit, Young's modulus, resilience or modulus of resilience, all this information, Young for example yield strength and offset yield strength, of course ultimate tensile strength, fracture strength, all kind of information we can get from a standard tensile specimen. So, suppose we assume that this is a typical stress strain diagram. So, first one is the linear component, and then it is a this engineering stress strain diagram reach the optimum point, and then fracture happens at this point. So, here you can represent the strain with the stress. So, this is the standard diagram stress versus strain that we can get from a uniaxial tensile testing of a specimen. But what information from this stress strain diagram we can extract? First is the proportional limit. So, up to certain point the deformation behavior of a particular component is the stress is proportional to the strain and represented by a linear line. So that we can say this is correspond to the elastic strain and this is the corresponds to the yield strength value. So, once just cross the yield strength value, then permanent deformation happens. So, we can say the plastic deformation normally happens in this during this process. Now, the slope represents the Young's modulus. So, stress is proportional to the strain. So, Young modulus can be represented by this stress versus strain, but this Young's modulus is defined we taking into the part of the curve up to that linear only the linear component. From the linear component we can measure the Young's modulus, the slope actually represents the Young's modulus. Then proportional limit of this limit almost in general it is equivalent to the yield point up to that point stress is proportional to the strain. Then resilience or modulus of resilience, that means what is the amount of energy actually absorbed during the elastic deformation. So, up to this point this is the elastic. So, this is the plastic deformation and this is the elastic deformation, plastic zone. Now, yield strength we define this is the point yield strength just start of the yielding happens at this point. So, that means after just crossing the elastic limit and then we start of the yielding process happens, that is defined by the yield strength. So, its yield strength can be as a boundary transition from the elastic to plastic deformation. And resilience or modulus of this area we just represents, if we calculate the area, the amount of the energy actually absorbed up within the elastic limit, and that energy represented by unit volume. So, this amount of the energy that is represented by the resilience, that is called resilience or modulus of resilience. And graphically if you have this stress strain diagram, if we simply estimate the area, that is the representation of the modulus of resilience. Now, ultimate tensile strength is the optimum point. Up to that point we can get the uniform deformation, elongation of the sample normally happens, and beyond the ultimate tensile strength normally the non-uniform elongation happens. So, that up to this optimum point is called the ultimate tensile strength, and further reduction in the this thing cross section and there is a non-uniform deformation happens up to beyond that point, and at a certain point the fracture happens, the fracture happens of the samples. Now, in this case the fracture strength is normally estimate the what is the total area covered by the up to the fracture point, what is the amount of the energy absorbed per unit volume, that is the representation of the fracture strength. So, this is the strength, but this is the from the if you know the fracture point and this strength is the fracture strength, but that area represents the fracture toughness we can say for a particular material. Now, offset yield point means in certain material the this curve is initial part may not be very prominent as a linear relationship. So, in that cases it is a transition from linear to non-linear is sometimes difficult. Then in that case we define it as a point, I think around 0.2% of the strain, that 0.2% strain we can draw the slope of the initial at the epsilon equal to 0 at this point. What is the slope? We draw in parallel to that slope, it cross up to that point. So, this point is represented by the yield point in cases which is not having the well defined transition from the linear to the non-linear part. So, this is the linear part and then it becomes non-linear. So, that transition is when it is not very obvious, then we assume the offset yield point and looking into the offset yield point, taking the offset yield strain value, and accordingly we can decide the what is the yield point just looking into what is the amount of the strain is 0.2%. Now, all this information we can gather from the stress strain diagram. Now, the mechanical properties normally evaluate that what is the ductility and brittleness and toughness. Normally toughness we have already explained that the area covered by the up to the fracture point, what is the amount of the energy is absorbed, that is representation of the toughness of a particular material. Now, ductility and brittleness is the measurement of this thing. Normally we measure the ductility is the equivalent to the in the elongation, maybe change of the length with respect to the original length or change of the cross section with respect to the original cross section. So, that is the measure of the ductility, and just opposite of ductility we can, that is the that is representation of the brittleness. Normally elongation is more than 5%, then we can say it is a ductile. It is less than 5%, we can say it is a brittle material. Now, once we have the engineering stress strain diagram, that means stress divided by initial cross section area and similarly strain with reference to the initial size, that is the engineering stress strain diagram, but that engineering stress strain diagram can be converted to the two stress strain diagram. The two stress strain diagram is mostly or always increasing order. So, here yielding point happens and then ultimate tensile strain and fracture strain, because in two stress strain diagram we can evaluate, we are looking into at particular point what is the instantaneous value of the cross section area, and based on that we can divide the stress value. So, that is why since further elongation beyond the yield point, there is a reduction in the cross section area. So, when there is a stress is by load divided by cross section area. So, if it is there is a reduction in the cross section area with the same load. So, therefore, stress is actually in increasing order. That is why we always get the curve something like of engineering increasing order, which is different from the engineering stress strain diagram. Now, this up to that point, this from yield point to that point is the uniform elongation, and from that ultimate tensile to the fracture point, that is normally happens the non-uniform elongation, and the necking starts at this point. The necking means the further there is a further and quick reduction of the cross sectional area and at this point. So, therefore, necking starts at this point and just transition point from uniform to non-uniform deformation zone. Then strain hardening parameter also sometimes is represented, because strain hardening is that after yield point there is a material, the strength actually increases with the straining of the component. So, in that case since material having some strain hardening effect, that means strain hardening means if further strain, the yield point value actually increases, the strength level actually increases by straining of a particular component. So, that is the because that effect is called basically strain hardening. So, different material having different kind of strain hardening effect. For example, titanium is having specific titanium alloy is having very low strain hardening effect. So, not much increment with this reference to the yield point value with further straining of a sample. So, these are the strain hardening properties also we observe, and then damping capacity. Damping capacity is basically the, if we look into the stress strain diagram, if we loading the sample in actual cases and then deformation happens, then we just release the load, and this is called unloading. Again we reloading it from this point, and this is loading, again unloading, that kind of behavior. So, therefore, it typically follow the loading path and unloading path may not be the same, it depends on the microstructural properties of a particular sample. But if this unloading path and loading path, when there is a several loading, it is this area is much high, it means it indicates that the damping properties of this particular material is very good. So, this area actually area is more having, that means having very good damping properties. If area is less, having less damping properties. For example, is a grey cast iron having good damping capacity, and if we look stress strain behavior of a grey cast iron with the loading unloading condition, we can get the stress strain diagram some this kind of behavior. So, because grey cast iron this area is more, and but in case of steel this area is very less. So, that means that is why steel cannot absorb the vibratory kind of load, that means damping capacity is not good. So, whatsoever with the loading unloading situation, it transmits the sounds, and of course, it creates the vibration, because it cannot absorb the vibration during this process. So, that kind of property is also important in certain application. Now, hardness also we frequently measure the hardness of particular material. That hardness actually represents the resistance to permanent deformation under static or dynamic loading conditions. There are several methodology or techniques to measure the hardness. One is the Brinell hardness test. It is a Brinell hardness test. In principle, the hardness test we measure in the form with the application of the load, and with the application of the load, and we follow certain indentation, and that we measure the indentation with a particular material, and that load divided by the cross section area, and that value we can compare with a certain scaling system, and based on the scaling we can say we indicate the hardness of a particular material. So, but there are different technology, basically different methodology to measure the hardness. So, first is the Brinell hardness test. In these cases we use the hard ball. Hard ball is used with the standard load, there is some standard load, and cannot be used either very hard or very soft material, and of course not suitable for the very thin sheet. So, Brinell hardness tests use the round shape ball, and then ball is standard load is applied to this ball, and ball actually indent to the surface, and we measure what is the indentation area, and that indentation area load divided by that indentation area in general, that is a representation that is equivalent to the representation of the hardness. Now, this Brinell hardness test is normally it is not applicable even material is very soft, or at the same time it is not applicable, it is not very hard. And of course, for very thin sheet this hardness measurement technique is not suitable. We can look into the other hardness testing also, testing methods. For example, Rockwell hardness test. In these cases we can use either very small steel ball or cone type, because we ensure with the even application of the small load some indentation it will create. So, basis is the increment, but we use this thing, and but in these cases we not directly measure the what is the absolute value of indentation with application, rather with changing the load what is the increment of the indentation due to increment of the load. So, here we use the increment of the depth with the increment of the load, that we can measure it, and then we can correlate in the hardness scale, and we represent the hardness. So, therefore, this should not be used on very thin material. Of course, this is not very suitable on very rough surfaces, or of course, it is not very suitable in non-homogeneous material, because the result is very much sensitive to the homogeneity of the structure, and it depends on the roughness of a particular material. So, therefore, this material is not suitable, and because in these cases the maybe indentation with change in the load, the depth of indentation may be very small, but we detect that depth with this changing of the load, and therefore, this used for actually this is very quick method, and it is very used for monitoring of the quality during the mass production system. This process is more suitable to measure the hardness, and because it is very rapid process. We can see also the Vickers hardness test, it is also similar to the Brinell test, but square based diamond pyramid is used. Here we use the square based diamond pyramid, but in these cases the increase in accuracy by the diagonal of the square impression. So, presence of the diagonal of the square impression as compared to the round steel ball, the indentation can be done or depth of indentation can be increased. So, that is why it is more accurate method, and of course, as compared to the circular section, and of course, it reaches the plastic deformation even at very low, even load is very small, then at least it reach some kind of the plastic deformation, and that is the principle. It is same to Brinell test, but the instead of the round ball we can use the square based diamond pyramid. In these cases it is used. Then several micro hardness testing, but micro hardness test is very small amount of the load is used, and of course, it is normally happens under the microscope under high magnification. So, we observe the under high magnification what is the indentation. So, one is this the Knoop test, indentation is measured using the microscope. Of course, Vickers test can also be used for micro hardness measurement. Apart from the this hardness measurement, and of course, compression test can also be done. We have discussed the tensile testing of a specimen, but at the same time in certain cases compression test is also important, and of course, combination of the tensile testing and compression testing is also significant to finding out the Boisinger effect of a particular material behavior. So, in general the compression test is more difficult than a tensile test, and of course, because test specimen must have a large cross section area as compared to the tensile testing, and this large cross section is required because to resist the bending and buckling during this process. So, definitely the compression test is may be significant when you try to look into the Boisinger effect of a particular material. Then torsion test, similar kind of the in normal stress and stress, we can that kind of graph we found out from the tensile testing specimen, but if we conduct the torsion test we can find out the relation between the shear stress and shear strength, and of course, in these cases the torsional load or twisted load is torsional forces is normally applied to find in case of the torsion test. Then bending test also typically performed to determine the ductility or resistance to fracture or the particular metal. We can conduct the bending test also. The purpose of the is to deform the sample into bending test is performed to test whether this sample can be deformed in a particular shape. And there are several other methodology for example, in mechanically, apart from all this standard tensile testing, compression, torsion and bending testing, there are also ring compression test, one of the testing method to evaluate the friction coefficients course. And then upsetting test also can also be done, and how material perform under compressive load, or this can be used for the measurement of the friction, and specifically in case of metal forming processes. So, both ring compression test, upsetting test normally associated with the metal forming processes to evaluate the coefficients of the friction of a particular material. And then apart from that, evaluating the plastic strain ratio of sheet material in different rolling direction, that is also that type of property sometimes need to evaluate, which is relevant to the metal forming process and basically sheet metal forming process. So, at different direction plastic strain ratio, because the sheet metal is pulled in uniaxial tension beyond its elastic limit, and we can at different direction we can find out the strain ratio in a particular direction, which is very important parameter in case of sheet metal forming process. And then with the static loading conditions, we can evaluate all the properties, even from the, if it is a dynamic, properties can also be measured, or mainly the application of the dynamic load. We can use the loading condition in the first, of course, what way. First thing is that if we test any sample in the dynamic loading condition, but first point is that what way we can represent the dynamic loading condition. One is the maybe impact load or rapidly change that impact load, or maybe load apply in such a way that a rapidly change in the magnitude, quickly there is a change in the magnitude. There is the one case. Second case is the either repeated cycle of loading and unloading. So, repeated cycle is loading and unloading, in the sense we are applying the load and then after half cycle just releasing the load, or frequent change in the mode of loading, that means we are applying the tensile loading and the next half cycle we can applying the compressive loading. So, like there is a change tensile, compressive, this type of loading condition. So, in practical applications, or material may be subjected all this kind of the dynamic loading situation, but if that is the dynamic loading situation, what are the testing methodology we can evaluate the properties of a particular engineered material or manufactured component. First is that to evaluate the dynamic loading condition, the impact test can be done. Impact test, the purpose of the impact test is to evaluate the fracture resistance of a particular material. So simply impact load is applied for particular material and then material fracture, then what is the energy of the what is the amount of the energy absorbed to fracture that particular material, that we normally measure in the impact testing methodology. So, there are two test methodology standard, that is a Charpy test and IIT test. Charpy test, we use the simply supported beam of that particular material, and we make a notch to ensure the fracture happens in the particular notch. So, in that cases, that is the Charpy test. And IIT test, of course, the similar kind of material can be made also in the form of a cantilever beam along with a notch. Both are impact testing methodology. Then of course, apart from that impact testing, the fatigue testing can also be done, because fatigue testing is the normally done by the application of the cyclic loading pattern, which is followed either entirely random variation in the stress. Basically, we need to, in a cycle, when there is a cyclic loading or dynamic loading condition, we need to find out the pattern of how there is a variation of the stress when we apply to the sample or specimen. So, with this model, first the variation of the stress, how it done, and with this particular mode of the loading condition is applied to the samples, and then we count what is the total number of cycles to induce the failure. So, therefore, we normally plot the curve that number of cycles, this is the number of cycles, and along with the stress value, corresponding stress value, and then we can find out that when up to a certain number, maybe in most of the cases infinite number of cycles, which is dependent around 10 to the power 8 cycles, what is the value of the strength, and that we can say this is the fatigue strength. Of course, this fatigue strength is less than that of the yield strength of a particular material, because yield strength is normally we can measure under static loading conditions. So, therefore, stress versus number of cycles we normally evaluate from the fatigue testing. And of course, this fatigue testing is also important another parameter, that is at which temperature we are conducting this test. So, at different temperature this curve will be different. so that as a function of temperature we can induce the this fatigue testing also, and finally we will try to find out this number of cycle versus the stress curve. Then apart from the fatigue loading, there is another type of loading, that is the creep properties. We have already mentioned the creep properties is simply properties at elevated temperature with the application of some kind of constant load, how material behaves in that situation. So therefore in this at a particular temperature, when you apply some constant load, the tensile specimen actually elongate, and that we try to measure this elongation, and until this elongation happens, until the rupture of the surface occurs. And of course this also failure happens below the yield strength value of a particular material. So therefore this creep properties is more significant for the design of a material process, for example, which is mainly applicable for the gas turbines, because gas turbine blade in power plant and high temperature application, or high temperature application means high temperature pressure vessel, in that particular cases this creep property, evaluation of the creep properties is very much significant. It may not be the important when we perform the performance of the engineering particular materials at a room temperature value. So therefore they are represented by the strain versus time curve, and of course this at a particular temperature. So we conduct the experiment with a closed chamber, maybe as a particular temperature, keep as a particular temperature, then we apply the application of the constant load, and then we use the, which is represented by the, what is the strain, particular strain means particular deformation in the form of and one particular time. So that output is important to evaluate the creep properties of a particular material. So apart from the other properties, the physical properties we already discussed, the other physical properties, the thermal conductivity, for example density, that normally use the standard experimental methodology. So that is not having the scope of discussion what are the standard methodology, but rather after engineer product, what are the in general in common we conduct the experiments for a manufactured component. So next we can, apart from this mechanical properties evaluation, microstructural measurement can also be done to some extent. For example, average grain size of a particular microstructure and their distribution is also important. So that is, we can use the optical microscope to measure the average grain size or distribution of the grains, but the methodology is used normally for average grain size, that is called the line intercept method. We simply draw a line, and this we count this line how many number of grains boundary it cross, and based on that we can measure the what is the average grain size using this methodology. So apart from that, residual stress in most of the cases manufactured component, which is the when there is a during manufacturing process, normally it is associated with either purely thermal condition or thermomechanical conditions. When the material is subjected to some kind of thermomechanical conditions, then there must be some amount of the residual stress generation. So that residual stress measurement also one important aspect in manufacturing technology also. So normally we can use the X-ray diffraction methodology to measure the residual stress of a manufactured component, but this X-ray method is XRD method normally used to measure residual stress particular surface. If you want to measure the interior, then X-ray may not be suitable in that cases. So in that cases Newton diffraction techniques is the more suitable technology. Even we can measure the residual stress along a particular depth direction of a manufactured component. Apart from that, chemical composition often we used for a metallic sample, we can use the energy disruptive X-ray analysis, EDX process can also be used for analysis of the chemical composition, and of course various phases of the component we want to measure in a sample, then we can use the XRD method also. So all this microstructural measurement may be associated with the manufactured component to analyze the or performance of a particular component. Now apart from that, the properties evaluation, this thing I am just shifting to the next module, next part, that is the statistical and data driven modeling approach. So once we go for some kind of modeling approach, mathematical modeling of what we can dealing with the statistical data without looking into the physical aspect of a particular process. So in that cases, if we have the data, then we can analyze the data by following some kind of the statistical and data driven modeling approach. But before that, the point is that what we can evaluate, we can extract the data which is maybe that data can be extracted maybe to evaluate the properties of a manufactured component, or the data can be evaluated during the manufacturing process to simply either monitor the process online or maybe it can be done offline monitoring of the process. But if you want to collect the data during the manufacturing process, then we need to use some kind of the sensor. So, sensor is to provide the data through some data acquisition system, and that sensor gives the output mainly in the form of the current, voltage, or maybe directly temperature can be measured also. So, therefore, this sensor data mostly used for online monitoring of the system, and that may be collected data may be passed through the robotic system if you use because when you do look into the monitoring system, then data is passed to the robotic system, and this robotic system, that robot can monitor the process. So, therefore, but that is the robotic process, how it evolves, that is not the point of discussion, but here discussion what we can collect the data and how we can utilize the data. So, sensor directly measure the technological parameters, or normally including the voltage, current, and maybe wire feed speed in cases. If in case of welding process also we can directly use the wire feed speed. So, this data mostly used for the online monitoring of a particular system. But apart from the sensor data, that is output in terms of the voltage and current. So, optical sensor can also be used, and in that cases we can use the laser also, laser system, and the laser beam is used, and that projected the scanning motion across the particular SIM. We can project the laser, and then this reflected data information can be captured by the CCD is used to feature of the weld joint in combination with the laser type. So, point is that laser based sensor also available for online monitoring of the system, and of course, sometimes CCD system can also be used to extract the data during the manufacturing process. Now, two types of the sensor for measuring normally use for measuring the current, and of course, that for measuring the current, that is called current shunt and the Hall effect. So, current shunt effect, this principle is that suppose let the current flow through a resistor and then measure the voltage drop across it, but the major drawback of this process is the resistor must be kept low. So, therefore, the voltage signal measure will be small and sensitive to a particular noise, but this is the current shunt method because we follow some kind of the parallel system, and but in case of the Hall effect, device in such that it is basically non-contact sensor and does not interfere with the current of the welding power source. So, that means if you use the welding system, then it does not interfere the welding power source. So, in that way we can use. So, if you want to measure of a particular manufacturing process, manufacturing system, the probably in that case is we normally use the device Hall effect to measure the current flow. Then other sensor of the measurement, maybe most of the manufacturing process may be associated with the measurement of the temperature. So, in that cases mostly use the thermocouple or maybe non-contact, maybe thermal vision camera or infrared thermometer can be used to measure the temperature. But main drawback is the necessary to maintain the constant contact with the workpiece during the welding process. So, that means during the welding process or any other manufacturing process, if you want to use the contact mode, that means of measuring temperature, that means if you use simply the thermocouple, then always it need to contact with the sample. Other is the infrared thermometer. Of course, it is not necessary to directly contact, it is a non-contact mode we can measure, but it is difficulty that uneven surface there if basically detects the thermal emissions from the surface. So, therefore, thermal emission is not proper, then it is very difficult to detect based on the non-contact mode using the infrared thermometer or thermal vision camera. So, therefore, but till if you compare the thermocouple based and the infrared camera to measure the temperature, that thermocouple, if you want to monitor the system, then thermocouple data is not suitable. Rather, the infrared camera measure, it is a more that data normally can use because there are some response time when you measure the temperature using the thermocouple. So, that respond in that quickly the response time is little bit more or it can be delayed in the monitoring system. So, therefore, the infrared thermometers have a faster response. So, it is more preferable to use for online monitoring of the system through which we can measure the temperature. So, therefore, according to the accuracy of the sensor system depends on the sensor themselves, and of course, the thermo model design. That means we have the capturing the data, but how we can convert the this thermal image in the form of a temperature. So, that needs some kind of the design, that kind of the model is required. So, therefore, in order to achieve precise thermal model, impact factors like the workpiece thickness, thermal conductivity, metal composition, etc., something have to be defined in advance, and accordingly we can make the model such that we can correctly measure the temperature by looking into all these factors. So, therefore, these sensors are also used for discontinuity detection, sim tracking and cooling rate measurement as well also. So, therefore, all these sensor data can be analyzed in such a then we can measure the discontinuous. If the during the process if the discontinuity happens, then we can detect by this temperature also, and of course, what is the cooling rate from the temperature measure, then that can also measure when you try to measure the temperature. Now, other sensor in fusion welding process, we normally use that ultrasonic, or not only fusion welding, in other processes also we can use the other type of the sensor. One is the ultrasonic testing of oils as one of the efficient method for the detection of the defects, irregularities, cracks, inclusion and other surface defects. One is the most proven technology is the ultrasonic method. So, this can be this ultrasonic method actually applicable for all type of the materials, but there is a also possibility of detecting very small irregularity. That is another advantage using this thing by looking into the pattern of this ultrasound. So, therefore, delay non-contact probe which is used, and actually that is reflected the ultrasound. So, we detect, first we pass the ultrasound, then there is a receiver, that reflected ultrasound is detected by the receiver, and we analyze this ultrasound pattern, and based on that we can detect the defect or other irregularities the process. Even it is possible to their existence of thermal gradients also in the material during the manufacturing process or after the manufacturing process, the thermal gradient can also be possible to detect through the ultrasonic testing technology. Data acquisition, then once we use different types of the sensor and to accurate the to collect the data, and of course, this data acquisition system can also be done once we do after the manufacture component. Even if we do the testing, from the testing from the testing results we can collect the data. For example, if you do the tensile testing of a manufacturing component at the different parameters, then we can get the data like tensile strength, elongation, ultimate tensile strength, yield strength, all kind of data can be evaluated from these things. Or other way, if we use some monitoring system, we can acquire the continuous data, but the data is collected in that continuous data during the manufacturing process. From the sensor, the data is collected some predefined sample rate. So, that means some with the gap with a certain frequency we collect the data, and then that data normally stored in the temporary memory, or maybe that is normally data acquisition system. Through the data acquisition system we can collect the data, and that the sample rate and the transfer of the data is normally controlled by the CPU monitor, or through the microprocessor we can control the data acquisition system. But we use the data continuous data, and we can analyze the data also. Apart from this continuous data, some discrete data points can be evaluated through different property evaluation techniques or different experimental techniques also. For example, strength properties of the weld joint or hardness, surface roughness or machine surface can also be collected measurement. These are the typical data we collect. Now, point is that different processes, either monitoring processes or offline monitoring processes, that means if you do some testing of the sample and or testing of the manufacturing components, we collect all the data. Now, point is that what we can analyze this data. So, that data analyze, there are several, that is called the process modeling, or we can say the mathematical modeling of the manufacturing process, but this mathematical modeling is completely different from the physics based mathematical modeling approach. Here we will be dealing only this kind of modeling will be dealing only the data on the data value without looking into the physics involved during the manufacturing process. So, for example, we can take one example, say oil quality modeling. So, few approaches in oil quality modeling. So, there are several methods. First is the sensor integration method. So, what we can integrate the different sensor data, that is the one methodology. Then artificial intelligence we can apply to find out the some parameters. Then the database different database techniques about analysis of the data and different statistical correlation is also possible if we analyze the data. And of course, finite element modeling, but the finite element modeling is the different this is a physics based modeling approach. This is the tool we use to model the manufacturing processes. And of course, apart from this data, and if we use the data image, capture the image, and if we analyze the image, then vision based system method can also be developed. So, these are the typical methodology for oil quality monitoring normally follow in case of type of the friction stir oiling processes. So, recently we are working in that area. The present research highlights, for example, we are trying to do the modeling of the oil quality using the Mendel's motor current signal. So, basically this is the data spindle motor current signal in case of friction stir oiling process. So, this data is collected by putting some kind of sensor, and that is from the sensor we can collect, and then this data can be related with the oil quality of the oil joint. So, in terms of the strength, or of course, modeling of the oil quality using the machine vision system. This machine vision system is basically we capture the image during the process, we analyze the image, and that particular image analysis we just try to link with the oil quality. So, following some kind of the data driven modeling approach. Then modeling of the oil quality using the sensor integration for force, that means from force sensor force measurement, and from the torque we can measure force and torque during the process, and we can link this force and torque with the we can model it in the sense that we just try to find out the correlation with respect to the input parameters in specific to the friction stir oiling process. This is just typical example of the data driven modeling approach. Now, few research techniques of the modeling approach, we can use the wavelet packet analysis, the standard packet available in the standard software, also wavelet packet analysis. Then Hilbert-Huang transform with the wavelet analysis. So, along with this is the one derivation from the wavelet analysis for a data driven modeling approach. Then we can use the fractal theory to characterize the signals, and by estimating what is the fractal dimension for a particular signal. Signal means is basically sensor data. So, that correlation can also be possible to explain, and that correlation can also be possible to explain using the application of the fractal theory. Similarly, neural network model can also be used. What is the input? We decide the input parameters, and in between, and we correlate the output parameters, and we can predict some data relate between by looking into the relation between the input and output parameters. Similarly, support vector matrix can also be one of the methodology to represent to define the or to express the oil quality, oiling quality in case of the mathematical modeling approach. So, once we look into that, collect all the data and different techniques, but if you look into the overall view, how we can do the process modeling and specific by even we have the lot of data, but and what we can do the process modeling and what we can optimize these process parameters. We can look into one example that, for example, the establishment of the input output relationship, for example, metal active gas oiling process. So, in these cases there are so many inputs, for example, the current, voltage, and the feed rate of the wire, that can be the input to the process, and output maybe strength or maybe some other parameter, strength, or maybe bead dimension, maybe the output of these things. But we can relate, always interested to relate what between the input and the output parameters. Now, what are the process we can use? We can use the simple regression analysis, and that regression analysis which was performed on the data actually collected by following the Taguchi design of experiments, that following certain norm of the experiments. And of course, this regression analysis is simply relate between the input parameters and what is the output, and that correlation. And of course, the adequacy of the regression analysis model is basically the feasibility of this model, parameters, all this thing analysis is normally done using the ANOVA method, the standard method available. All the statistical information will be available using if we apply some ANOVA techniques. So, RA model was then regression analysis is basically embedded into an optimization algorithm. So, this RA model is simply the relation between the input and output that can be integrated with some optimization algorithm to determine the optimal process parameters for a well bit geometry specification. That means, if we know what is the relation between the input parameters for a particular welding process, the current voltage and this feed rate, and what is the output parameters, these things by using this relation. Now, we can optimize this, we can optimize, suppose we are looking for a desired weld dimension, we want to get this dimension. Therefore, we utilize the relation between input and output through regression model analysis, and then if this is the desired input and output, and then we passes through it through the optimization algorithm such that this for particular to get the particular weld dimension, if we expect what should be the input parameters for these cases. So, that normally done by integrating the optimization algorithm. So, therefore, if we integrate with the optimization algorithm, that predicts the process parameters for the weld bit geometry. If we looking for a particular weld bit geometry, then we can find out what should be the input parameters for a particular welding process, but with the help of the optimization algorithm. And of course, before doing that, we need to establish the relation between input and output through the regression model. So, regression may be linear, or it can, the relation can be non-linear also. So, therefore, input parameters of MAG welding process, maybe you can say the welding speed, welding voltage may be another parameter, wire feed rate is another parameter, nozzle to plate distance is the another parameter, and torque. These are the all input parameters. And now, output parameters or responses, we can say height, bead width and bead penetration. So, height, this is the output parameter. So, we get, if this is the input for a particular set of the input, we can get particular output in the form of the weld bead height and penetration. Of course, so in these cases 3 levels are considered, and therefore, we can design this in a full factorial design if we consider the 3 level of our experiments. So, basically 3 different values of the all the input parameters, then there is a lots of experiment will be required if we go for the design of experiment for a particular process. So, but if we follow the Taguchi design of experiment, therefore, that suggests some kind of the limited number of experiments is actually required. So, we can reduce the number of experiments in that case. Now, point is that if we follow this kind of try to establish the relation between the input and output through some regression or some statistical model between this input and output, then in that cases the reliability of this relation will be depend on large number of experiments. So, therefore, in these cases large number of experiments is actually required. Now, if we integrate the optimization algorithm to find out the optimum set of parameters for a desired weld bit geometry, desired output, then in that cases the optimization the algorithm can be used the GA based evolutionary algorithm, GA genetic algorithm, differential evolution, simulated annealing can also be used. And of course, in these cases the set of mathematical equations, the linear, curvilinear or logarithm relation between the input and output is required. So, therefore, this relation is develop this relation between the variables and the weld bit geometry in gas metal arc welding process. So, therefore, this in the form of the linear, curvilinear or logarithm relation can establish between the input and output. Now, optimum algorithm determines the optimum values for the process parameters with respect to any given bit geometry. So, optimum algorithm actually try to decide the range of the parameters, and then it check for a particular set of the input parameters is the what is the output parameters by checking the already established the relation. Then if output parameters is not desirable in these cases, then it it test for the next set of population. So, that is why it moves and try to estimate what is the optimum parameters for a particular desired output. So, then determine the best process variable through minimization of the error function with respect to the specification. So, the optimization algorithm is calculate the one specific for a particular set of the input, it calculates the one particular set of the output. Then that output is compared with the desired output, compare it, create the error, and that with the over the iteration it tried to minimize that error. So, that is the overall procedure of the optimization algorithm. Now, Taguchi design of experiment, we normally follow that a model is checked by the analysis of the ANOVA table, normally variance with confidence intervals 95%, and all the correlation factors among different parameters or set of parameters is tabulated using the standard ANOVA table. Therefore, choose to from this analysis there is a choose, maybe one analysis can be done some linear relationship, then choose the superior model among the linear curvilinear algorithm. If we start with the input relation between input and output in the linear by using some linear function linearly fit, or we can use some curvilinear model, or we can use some logarithm model. So, based on the ANOVA table results, we can choose which one is the best representation of the statistical curve between the input and output parameters. So, therefore, after that we establish the relation between the input and output parameters, then few experiments are needed to test the mathematical model whether it is giving the right output or not. So, that is how you can validate this relation. So, therefore, mathematical models furnish to provide one-to-one relationship between the process variables and the weld dimensions, but can be used in the two ways. One is the that already discussed, the predicting the bed dimension based on the given welding variables. So, we can predict particular dimension using the given variables, or other way also we can determine the reverse things, we can find out which is possible to determine the process parameters if you want to get a particular weld bed specification. So, therefore, in order to determine the proper values of the welding parameters, a set of nonlinear equations are to be solved simultaneously, and that way, that sort when you try to look into this can be performed by integrating it with some optimization algorithm. Now, we can look into that some application of this thing. For example, process parameters in FSW process, the tool geometry. There are different types of the pin length, pin diameter, shoulder diameter, thread profile, tool tilt angle, all are the parameters which is maybe input parameters, tool geometry specification. And apart from the tool geometry, welding parameters are also responsible. So, this is corresponds to friction stir welding. Now, welding parameters are the tool rotational speed, welding speed, tool plunge depth, and the dwell time. These are the all are the welding parameters. So, these all the input parameters. So, this input parameters is used to predict either different data driven modeling approach, neural network modeling approach, or other statistical approach can be used to predict the ultimate tensile strength of a weld joint, yield strength of a weld joint, and percentage elongation of a weld joint, or what is the hardness of an weld joint. So, this is the output from the model, and these all are the input, and this relation is established through some statistical or data driven modeling approach. So, this is all about the different parts of the approach normally we follow in the statistical or data driven modeling approach, but this course is not exactly focused on the analysis of the different types of the techniques and data driven modeling approach is used. Rather, I have discussed this point just to know there is other direction of the modeling approach, but our focus will be in the next other modules to look into the physical aspects of the manufacturing process and to explain the different type of the manufacturing process and their modeling approach by looking into the physical phenomena associated with the particular manufacturing process. So, thank you very much for your kind attention.